For decades, Moore's law has been the bedrock of technological progress, driving an exponential increase in computing power. But are we finally reaching the fundamental limits of this incredible trend? Let's analytically explore the challenges and the groundbreaking solutions emerging from the world's brightest minds. Moore's law, an observation made by Intel co-founder Gordon Moore in 1965, predicted that the number of transistors on an integrated circuit would double approximately every 2 years. This wasn't a physical law, but rather a self-fulfilling prophecy that guided the semiconductor industry for over half a century. It fueled an era of unprecedented innovation. This relentless doubling meant that computers became exponentially faster, smaller, and cheaper with each passing generation. From bulky mainframes to powerful smartphones, every technological leap we've witnessed owes a significant debt to the consistent march of Moore's law. It transformed industries and reshaped our daily lives. For decades, the primary way to achieve Moore's law was through aggressive miniaturization. Engineers found ingenious ways to shrink transistors, the tiny on-off switches that form the basis of all digital electronics. Each new process node, like 90 nanometers, 45 nanometers, or 7 nanometers, represented a significant reduction in transistor size. Smaller transistors meant more could fit onto a single chip, leading to increased processing power and efficiency. This scaling also reduced manufacturing costs per transistor, making advanced technology more accessible. It was a virtuous cycle of innovation, driving down prices while boosting performance. However, the laws of physics are immutable, and we are now confronting them head-on. The fun fact is that shrinking transistors is reaching atomic scale limits, where components are only a few atoms wide. At this scale, quantum phenomena, like electron tunneling, begin to interfere with reliable operation. Heat dissipation also becomes a monumental challenge. Packing billions of tiny, active components into a small area generates immense heat. Furthermore, the precision required for manufacturing at these scales pushes current lithography techniques to their absolute boundaries. The economic cost of developing new, smaller nodes is also skyrocketing, making further planar scaling increasingly unsustainable. Recognizing these limitations, engineers are now exploring revolutionary new architectures to continue advancing computing power. One prominent solution involves moving beyond a purely two-dimensional layout. This shift is critical for maintaining performance gains without relying solely on shrinking individual components. A key innovation is 3D stacking, where multiple layers of chips are vertically integrated. Instead of spreading components across a flat surface, they are stacked on top of each other, connected by incredibly short, efficient pathways. This approach dramatically increases transistor density within the same footprint. Technologies like high-bandwidth memory, HBM, and chiplets are prime examples of 3D integration. HBM stacks memory dies vertically, providing much faster data access for GPUs and high-performance processors. Chiplets allow different functional blocks, like CPU cores and I/O controllers, to be manufactured separately and then stacked or interconnected, optimizing production and performance. Beyond silicon, researchers are investigating entirely new materials with superior electronic properties. Graphene, a single layer of carbon atoms, offers exceptional conductivity and strength. Other 2D materials, like molybdenum disulfide, show promise for ultra-small and energy-efficient transistors. These materials could potentially overcome some of the physical limitations of silicon, enabling faster switching speeds and lower power consumption. However, integrating these exotic materials into existing manufacturing processes presents significant engineering challenges that are still being actively researched. Looking further into the future, entirely new computing paradigms are emerging, promising to solve problems currently intractable for even the most powerful supercomputers. These approaches move beyond the classical binary logic of zeros and ones. They represent a fundamental shift in how computation is performed. Quantum computing harnesses the principles of quantum mechanics, such as superposition and entanglement, to process information in fundamentally different ways. Instead of bits, it uses qubits that can represent 0, 1, or both simultaneously. This allows for an exponential increase in processing power for specific types of problems. While still in its early stages, quantum computing holds immense potential for breakthroughs in drug discovery, materials science, cryptography, and complex optimization problems. It's not a replacement for classical computers, but a powerful complement for specialized tasks, opening up entirely new frontiers of scientific exploration. Another exciting frontier is neuromorphic computing, which aims to mimic the structure and function of the human brain. These chips are designed to process information in a highly parallel and energy-efficient manner, much like biological neural networks. They excel at tasks like pattern recognition and machine learning. Neuromorphic systems could revolutionize artificial intelligence, enabling AI models to run with significantly less power and greater speed. By moving computation closer to memory, they overcome the von Neumann bottleneck that limits traditional computer architectures, paving the way for more intelligent and autonomous systems. Moore's law, as we knew it, may be slowing down, but the spirit of innovation it embodied is stronger than ever. The future of computing won't rely on a single breakthrough, but on a multifaceted approach combining advanced packaging, novel materials, and entirely new computational paradigms. This evolution ensures that technological progress will continue, albeit in new and exciting directions. From the atomic scale to the quantum realm, the quest for more powerful and efficient computing continues unabated. The challenges are immense, but the solutions being developed are even more extraordinary. We are entering a new era where ingenuity will redefine the boundaries of what's possible. The journey from silicon scaling to quantum and neuromorphic solutions is a testament to human innovation. We are witnessing a pivotal moment in computing history, where the very definition of a progress is being rewritten. The future of technology is not just about making things smaller, but about making them smarter, more interconnected, and fundamentally more powerful. From silicon to quantum, follow for more chip secrets and join us as we explore the cutting edge of technology. Subscribe, like, and share this video to stay informed about the incredible advancements shaping our digital world.